Alright, so today's lecture, today's video is all about the dissolving process. What does it mean for something to dissolve? What affects whether or not something will dissolve? What affects how fast something is going to dissolve? So this is the topic of the day. Let's first remind ourselves the difference between solute and solvent. So if I have a beaker of, well, if I just have a beaker and I have some liquid in there, let's say the liquid is water, and I have a cube of sugar. The liquid, the water in this case, is going to be the solvent. So this is going to be the solvent. Whatever goes in our solvent is going to be our solute. So in terms of biological molecules, water is called the universal solvent for life because you dissolve things in water. So whatever you put in water is going to be your solute. Whatever you use to dissolve the water is going to be the solvent. So here, if this is a sugar cube or a cube of salt, which is kind of odd, but whatever it is, how does it dissolve? What causes it to dissolve? If we're just talking about any random object, could be anything. It could be sugar, could be salt, could be a vitamin. What's going to make that chunk dissolve? So here, let's blow up our cube a little bit. Our cube is going to be made of lots and lots of atoms, which I'm going to say are smaller cubes. You guys will have to use your imagination here a little bit as best we can. So each cube, we can almost think of each small cube inside of here, we can think of as being an atom of, let's say, salt. Actually, you know what? Let's not use salt. Let's just use the generic thing. The big cube is going to be what we're trying to dissolve. So the big cube is what we are trying to dissolve. Each individual little cube is going to be a molecule. So the big cube is made of lots and lots and lots of different molecules stuck together. Each little cube inside I should say square because this is two-dimensional. So each little square is a molecule. So when we put this big cube, this giant clump of molecules in that solvent, what's going to happen? Is it going to dissolve? And if so, why? We're going to say that it is going to dissolve. And we're going to say the reason that it's going to dissolve is because the molecules of water, let's redraw our big cube down here now that it's all nice and labeled. Almost forgot to do that. Oh, big cube, why do you take so long to draw? There's our big cube once again, drawn nicely and neatly. If we put it in water, so big cube, our giant chunk of molecules is submerged in water. So we'll say cube submerged in water. Okay, what's going to cause the cube to dissolve? And what that means is each of these little squares, each of these molecules are going to break apart from one another and they're going to become evenly distributed throughout the liquid. Why does that happen? So the reason is because the water molecules will, as long as they have enough energy, will get in between two molecules in the cube and they will break it apart. So let's write that here. So water molecules will break apart the cube. And really this is kind of a crystal, I suppose. But we'll just continue using the word cube since that's what we've already used. When that happens, as long as it does break apart evenly, the cube molecules, whatever this giant thing is, whatever this giant crystal is, the molecules of that crystal will be evenly distributed throughout the solution. So what's going to affect how fast this happens? What's going to affect, yeah, really, I guess how fast this happens is what we're going to talk about today. Okay, so once again, the water molecules cause this cube to break up. They cause this giant clump of whatever to break up. I'm going to use an example here, and I'm going to use something to grab it. If I have a chunk of dry ice, which is what this is right here, it's basically a giant collection of several moles, actually not several moles, probably half a mole of carbon dioxide molecules stuck together. If I were to put this chunk of dry ice, this chunk of billions and billions of CO2 molecules in water, it would break up. Each molecule would become separate and independent. They would be evenly distributed throughout the solution of water, and we would get some chemical reaction, I would imagine. So what's going to affect how fast that happens? The first thing that's going to affect how fast that happens is surface area. So let's start the top of our thing here by saying surface area affects how fast something will dissolve. And when I say surface area, I'm not talking about surface area of the solvent, really. I'm talking about surface area of the solute. So the surface area of the solute is what is, going to determine whether or not something's going to dissolve. So the more surface area a solute has, the faster the solute will dissolve. All right, and so I shall show you a very concrete example of that, I hope anyway. So if you guys need me to pause, raise your hand now, or pause it yourself if you're watching at home. I didn't make them, I bought dry ice this morning, and I have two evenly sized. It's very difficult to see because this is white paper, my mistake. These two chunks of dry ice were the same size. They were the same size. They're not anymore because I crushed this one up. In this chunk of dry ice, only the molecules of dry ice on the outside here are exposed to the air. This chunk of dry ice has been crushed into, I don't know how many pieces, many pieces. All the pieces, all the separate pieces now have individual sides. So when you crush something up, more and more and more and more of that, whatever it is exposed to the air. And if we dissolve it in water, it's going to be exposed to the water. I have a few samples of the stuff here. My first sample, I'm going to dissolve the chunk of dry ice in this beaker. The crushed dry ice is going to be in this beaker. We're going to see how long it's going to take the chunk to dissolve, and we're going to see how long it's going to take the crushed dry ice to dissolve. The faster the solution change between the two beakers, or the faster the color change, I'm sorry, the faster the dissolving process will have happened. So I'm going to have to try and do this as carefully as I can. It's just me. All right. There we go. All right, so it's very difficult to see the color change here because there's dry ice fog in the way. Let's see if we can get this thing. And actually, you know what? One of our reactions is already over. This reaction is done. All the dry ice in the powder form has already dissolved. It's not bubbling anymore. The fog is just kind of staying over the top. Our large chunk of dry ice, which was the same size before I crushed it up, is still in the process of dissolving. So that happened a lot faster than I thought. The surface area actually affected how fast it would dissolve a lot faster than I thought. That was a very interesting experiment. Well, I guess that's that. All right. I'm going to let these kind of continue over here. We could still hear a bubbling time to time. Yeah, we can definitely still hear bubbling. So when you crush something up, if you crush up sugar, if you crush up salt, if you crush up pepper, whatever it is, it's going to dissolve faster in whatever it is you're trying to dissolve it in. So if we turn that into a cogent sentence, crushed up solute has more surface area. Exposed to the solvent meaning it will dissolve, meaning it will interact with the solvent more, I should say. And dissolve faster. Okay, so that's that. We can even take another quick look at our two solutions here. Crushed up, gone. Not crushed up, still there. I weighed them this morning. I had 21 and 20 grams of dry ice. So they were really quite close to the same mass of dry ice. This, when I crushed it up, obviously is dissolved quite a bit quicker. I didn't get a nice color change on it though, which I'm a little disappointed about. I haven't done this one either. Oh, I'm getting a little bit of this one. Oh well. So that is surface area, and that's the effect surface area will have on whether or not something will dissolve and how quickly it will make something dissolve. This is probably sounding a lot like the reaction rates and the equilibrium videos, because the same factors that affect those things affect here. If I'm gonna give you 5 seconds to guess what else is going to affect how fast something's going to dissolve, you might very quickly come up with temperature, because temperature will affect how quickly something will dissolve. So temperature, we know, is the average. Whoa, it's not even on my screen. Hang on a second. Let me fix that real quick. Is it now? Kind of. Close. Close enough. So temperature. We know temperature is the average measure of kinetic energy for, anything. If you have a sample of air, the temperature of that air is how fast, how much energy the air molecules have, how fast they're moving. In a solution, the higher the temperature, the faster the molecules in that solution are moving, the more energy they will impart onto the solute. So we'll just say more temperature, which is really an awful word. I should say higher temperature means molecules will have a higher average kinetic energy, which means molecules in a solvent will have higher kinetic energy So if they have more energy to deliver onto our cube. Let me bring our cube back one more time. So here's our cube. You know what? Let's even draw the cube again. I think the cube's gonna really come in handy today. So here's our chunk of dry ice. We've got lots and lots and lots of molecules of dry ice or carbon dioxide making up that chunk. So here's our chunk once again. Let's draw a nice big chunky beaker for our chunk. So the water molecules are going to be, well, I'm going to assume that the water is a solvent for us. They're going to be hitting the chunk with some energy. If they have a high temperature, they're going to have a lot of energy, which means they're going to have more than enough energy to break this cube up into all of its pieces. If these water molecules are really cold, if they're not moving that fast, they may just slowly bump into the chunk and bounce off without doing anything to the chunk. But if they're really hot, if they have a lot of energy, they're going to blast into the chunk and they're going to break it up into smaller pieces. There we go. So molecules with higher kinetic energy have more energy available to dissolve whatever it is they're trying to dissolve. Oh, I don't know if I spelled available right. To a chunk. I should say particulate instead of chunk. Chunk is just not a scientific word. It's an awful word at that. Of solute. So this is how temperature affects whether or not something to dissolve. Blah. I can't grammar today, guys. Give me a break. So the last factor that's going to affect how fast, how readily, how often, whatever something dissolves is pressure. So this does sound an awful lot like equilibrium and reaction rates. So we've got pressure affecting how things dissolve. In fact, pressure has a huge impact on whether or not a gas like oxygen or carbon dioxide or nitrogen will dissolve in a liquid. So if we draw a beaker and we draw some water, which is going to be our solvent, we can imagine molecules of carbon dioxide being dissolved in this liquid. So sodas or any sort of carbonated beverages are made by taking carbon dioxide and dissolving it in the water. At some point, and then it's sealed. At some point, you're going to open that beverage and you're going to see the carbonation come out. You're going to see this carbon dioxide gas come back out. How do they get the carbon dioxide gas into the liquid? How do they get it to stay in the liquid? By using lots of pressure. So higher pressure, very simplistically we can say higher pressure forces solutes to dissolve in solvents. So if there's a lot of pressure coming from somewhere, it could be a machine, could be a person, could be, who knows where. If a lot of pressure is forcing that carbon dioxide gas into the liquid, well, the carbon dioxide gas is just going to go where it has to go. It's going to go into the liquid. In a soda, see if I can draw a can. If I can't draw a can of soda, boy, that's bad. So we're going to leave it uncapped just for a moment. It's filled with liquid because it's a soda, and it's got sugar and it's got whatever flavoring Pepsi or Coca-Cola or whatever company uses. So it's got sugar, it's got flavoring, and then they want to give it just a little something else, so they pressurize it with CO2. Tons and tons of pressure. Not just regular atmospheric pressure that we're used to every day in the room or outside or whatever. A lot of pressure. They force that carbon dioxide in there with a lot of pressure, and then they cap it. So they force lots of CO2 molecules to be trapped in here, and it actually, if we look at the reaction, when that happens, it's CO2 plus water is in equilibrium with carbonic acid. So that's the reaction of how you get soda in water. When you open that soda, So this is a closed soda. When you open it, the pressure on the inside of the can drops dramatically, and all that CO2 gas escapes. So higher pressure forces things to dissolve, mostly gases, but not just gases, could be anything. Lower pressure is going to do the opposite. It's going to let things come out of solution. It's going to allow the solute to come out of the solvent. So that's really simplistically in a nice, short, succinct video. Let's go back and let's review what we just talked about on a, let's use a separate piece of paper, why not? Let's use all the paper today. So what did we talk about? We talked about what will affect how things dissolve. What will how things dissolve? No, not at all. What will affect how things dissolve? I don't know if that's affect or effect. It's not been my morning, guys. Give me a break. What will affect how things dissolve? If you want to know what I wrote up here, I don't know if it was on the thing, I wrote, what will how things dissolve? Don't tell your English teacher. Good Lord. Okay, so what will affect how things dissolve? I'll give you a second to think about it. We should have come up with the surface area of, what was it, solute or solvent? It had better have been the solute. It's going to be the temperature of our solvent, and I suppose temperature of the solute as well. And the final thing would be the pressure. So those are the three things that are going to affect how something dissolves. I hope these notes were somewhat helpful. If they were not, please give me a little feedback. What will help you in the, what will help you in the future? Probably me leaving this on the screen would help a little bit so that you guys actually have time to write it down and look at it. Have a fantastic